As in the 1D case, strain in 2D is defined in terms of the displacement function. In 2D, the displacement function has two components, dx and dy. There are three types of strain to define. Normal strain in the x direction, defined as the partial derivative of dx with respect to x. Normal strain in the y direction, defined as the partial derivative of dy with respect to y. And shear strain, which is a measure of the change in angle from 90 degrees between the horizontal or x-axis and the vertical or y-axis in the stressed object. Looking at the first diagram, the x-axis has rotated theta x degrees, and theta x is positive, and the y-axis has rotated theta y degrees, and theta y is negative. The total change in angle between the x and y axes is theta x minus theta y. Using the small angle approximation, theta x equals the partial derivative of dx with respect to y, and theta y equals minus the partial derivative of dy with respect to x. So theta equals the partial derivative of dx with respect to y plus the partial derivative of dy with respect to x. Thus, the sum of these partial derivatives equals the shear strain. In the second diagram, note that when the object rotates counterclockwise, both theta x and theta y are positive, so that the computed shear strain is 0, as it should be. In 1D, the strain tensor is the directional derivative, and in 2D, the Jacobian, the matrix of partial derivatives shown, computes the directional derivative. That is, the Jacobian maps a unit vector representing a direction at a point xy to the directional derivative of the displacement function at that point. So it's a good candidate for the strain tensor. However, there is a problem. When an object is translated, it does not produce any strain in the object. The displacement function is constant, and all the partial derivatives are 0, and hence the Jacobian is 0, so this is good. When an object is rotated, again, it does not produce any strain in the object. However, the displacement function is not constant, and the partial derivatives making up the Jacobian are not 0, and this is bad. The solution is to partition the Jacobian into a strain tensor and a rotation tensor as shown. We will only use the strain tensor. Note that the diagonal of the strain tensor is the shear strain, the angle theta, divided by 2. Mathematical physicists prefer to use the tensor notation, i.e. the symmetric strain tensor shown, while engineers define strain using three numbers: the partial derivative of dx with respect to x, the partial derivative of dy with respect to y, and theta, the partial derivative of dx with respect to y plus the partial derivative of dy with respect to x. We will follow the engineering convention. We've covered the physics and won't need to think about stress and strain for a while until we get to the boundary conditions for the exercise. However, there's still a lot to do in terms of manipulating the equations. It's all by rote, cookbook style, but the equations are pretty formidable. So let's relax a minute before starting. And we're going to change notation and call the components of the displacement function d, u, and v to match the literature and to reduce the number of subscripts in the equation. Ultimately, we want to write the stresses in terms of the displacement functions, i.e. derivatives of the displacement functions u and v. So we start with Hooke's law, shown at the top of the page, and invert it to get the stresses in terms of strains. Now we can substitute definitions of the strains in terms of partial derivatives of the displacement functions to get the desired expressions for the stresses in terms of derivatives of u and v. Recall the equilibrium model for stress in a stressed object we developed in the previous video. We replaced the stresses by the expressions in terms of partial derivatives of u and v. Performing the indicated differentiations, we have the final form of the equilibrium model for a stressed object in terms of u and v. What next? The Fdm substitutions, of course. We make the Fdm substitutions for the partial derivatives of the displacement functions. This is all by rote, a cookbook procedure. Finally, with dx equaling dy, we can simplify the model as shown. We're now ready to work some examples, but we'll save that for the next video.